Hey, Calc students, this is Mr. Beck. Today we're going to be finishing our discussion about some basic series. We're talking about alternating series today, as well as the ratio test and the root test. So let's kind of begin by taking a recap of where we've been. In 8.1, one of the big things that we talked about was really just sequences in general and what sequences were. And those are really just kind of like a pre-calc review. 8.2 is where we started talking about some specific series, and the big series that we talked about were geometric series. When it came to geometric series, the geometric series said that if the absolute value of our ratio is less than 1, then we have what we call convergence, and if the absolute value of the ratio is greater than 1, then we have divergence. What do we mean by convergence and divergence? Well, when it comes to convergence or divergence, that says, do we have a sum or not? So if we have convergence, then we do have a sum. If we have divergence, there's no sum. So that kind of like goes to the overall general question of what is it that we're doing in this chapter? Our goal is, with a series, can we find a sum? Is there a sum that we can find? And I want to know what that sum is. So the geometric series allows us to say, is it possible for us to have a sum or not? And if we do have a sum, we can find that sum by our sum is a sub 1 over 1 minus r. That would be for our infinite series. After we talked about geometric series, then we said, okay, well, we do have a specific test that tests for divergence. That would be the nth term test. So if the nth term is not 0, then we know that we have to have divergence. Then we began where we talked about the integral test. So when it comes to the integral test, we said that if we compare, or if we use the integral of that function, then if the integral converges, then the sum converges. If the integral diverges, then the sum diverges. So both converge. Let me actually write it that way. So both converge or both diverge. Now I'm going to go a little bit off of the pace that we had before. Is why do both converge or both diverge? Well, the reason for that is because if our sum, oops, wrong direction. If our integral converges, then the sum underneath it would also converge. If the integral diverges, then the sum above it, if we shift over the sum, will diverge as well. So we could look at this as a combination of Riemann sums and integrals together. So anyway, that was our integral test. And from the integral test, that's where we got our p-series test. So with our p-series, if we tried to integrate 1 over x, that integrates into the natural log of x, which the natural log of infinity is still another form of infinity, so we have divergence. Versus if we have 1 over x squared, that integrates into negative 1 over x, so we have 1 over infinity, which is essentially 0. So the p-series test is born from the integral test. Now, the integral test, what I mentioned was the limit, or not the direct comparison test. And I sort of jumped over that, so I apologize. The direct comparison test says that if the larger sum converges and the shorter sum converges, or if the shorter sum diverges and the larger sum diverges. So that's our direct comparison test. Then we had the limit comparison test, and the limit comparison test said that, okay, let's compare the rate of change. So let's compare the rate of change with a known function. And if they change at the same rate, they will either both converge or diverge. So both converge or diverge. So that's a very, very quick recap of where we've been so far. Now, all of those involved positive series, which is where I'm going to go over here. All these involve positive series. So with the positive series, if the integral, or if the series is all positive, then we're seeing that our terms are going to decrease like so, and eventually they have to decrease to 0, or the infinite applies. Well, what happens if all of our terms are negative? Then if all the terms are negative, then each term has to increase and still approach 0 as well. So with that said, what happens if we have terms that are both positive and negative? We still have to approach 0 essentially, or eventually, to be able to have a sum, and that's what we're going to deal with today. So I can pause for just one quick second. All right, and I'm back. So what I had said was we were going to be talking about alternating series today. So what happens if we have an alternating series, meaning we have terms that are both positive and negative, and successively positive and negative? One of the approaches that we're going to take is this alternating series test, where we're going to say, okay, the alternating series is going to occur because we have -1 to a power, whether it's -1 to the n minus 1, -1 to the n, or -1 to the n plus 1. That's what's causing the alternation between the terms. So with our alternating series, if each successive term, and this is again, let's ignore the negative, let's just focus on what the rest of the series is, because we have all these tests that allow us to determine what happens if they're all positive series. So let's use this information to our benefit. So let's go ahead and ignore the alternating, say, okay, if each successive term is less than the previous term, which means the series is non-increasing. Let me rephrase that, less than or equal to the successive term. That's where you have a non-increasing function and the limit approaches 0. So if both are true, then we can say by the alternating series test that the sum that we have is going to converge as well. So let's take a look at what we have here. So with what we have here, if I start plugging in terms, and everybody, I strongly encourage you to plug in terms so you can get a feel for what that series is doing. It actually builds a very strong number sense, so please, please, please do that. So if I plug in 1, I get 1/3, then -1/6, positive 1/9, -1/12, and then plus, et cetera, et cetera. So if I take a look at this and say, okay, the main function that I'm working with is the 1/3n. Let's ignore the alternating portion. I can say that 0 is less than the successive term, which is less than the term that we're looking at. We can see that 1/6 is less than 1/3, 1/9 is less than 1/6, 1/12 is less than 1/9. How would we know this? And then we could use kind of a modified version of L'Hopital's rule to get an idea of what's going on, meaning that the rate of change in the numerator is smaller than the rate of change in the denominator. Therefore, the denominator is growing faster, and our function is going to be non-increasing. Now, this isn't like a pure overall logic, but this is a very quick way for us to be able to determine if the numerator or denominator is growing faster. So that's true. We have non-increasing. Then at the same time, we also have the limit is 0. And we know that because if we plug in infinity, we have 1/infinity, which is essentially 0. Therefore, we have convergence by the alternating series test. So once again, the two things we're checking for is non-increasing and the limit as we approach 0. Moving right along on our second test. So we have n, so we have a polynomial over a exponential. Now, if you know anything about polynomials over exponentials, the polynomial should be growing slower than the exponential. So therefore, we should have some convergence by the alternating series. But let's go ahead and prove this by the alternating series. Now, the reason why it alternates, if we factor out that -1 to the n minus 1, this is the rule, the a sub n, that we're going to look at. We plug in our terms. First term is 1, second term is -2/3, positive 1/3, -1/27, et cetera, et cetera. The numerator is growing at a slower rate than the denominator, so this shows the non-increasing. And then we also have the limit is 0. And how do we know that limit's 0? This is a perfect opportunity to, let me just jump back and say, this is a perfect opportunity to use L'Hopital's rule. So by L'Hopital's rule, this will be the limit as n approaches infinity of 1/3 to the n minus 1 natural log of 3. So some good derivative practice for us. But now that limit is going to be, that limit is going to be 1/infinity, which is 0. So since the limit is 0 and it's non-increasing, it converges by the alternating series test. On to the next one. So with our next problem, we have something that we haven't really faced before. And so this is a perfect opportunity to explore some deeper mathematics or like other relationships that force us to have an alternating series. That relationship is going to be the cosine of n pi, where if we plug in 1, we get the cosine of pi, which is -1. If we plug in 2, cosine of 2 pi is +1. Plug in 3, cosine of 3 pi is -1. So that's what's creating our alternating. Now, if we plug in numbers, we have 3 over the natural log of 4, 6 over the natural log of 8, 9 over the natural log of 12. And I don't know about you, but without using a calculator, how do I determine if this is increasing or decreasing? Well, that's where the L'Hopital idea, by figuring out the rate of change in the numerator, we could see that that is going to be 3, where the rate of change in the denominator, this is going to be 1 over 4n. They're actually just 1 over n. So since 3 grows at a faster rate than 1 over n, we could see that this is an increasing function because it increases as we have divergence. Example number 4. On example number 4, this is kind of a fun one for me. This is one that I just really wanted to use to explore different ideas. So if we plug in numbers, because this is really weird, we get -5, then we get 0, because the sign of pi is 0. Then -9/23, then we get 0. 13 over 71, 0. And essentially, this is a non-increasing function. And a lot of people, like right from the beginning, say, why don't we just say decrease instead of non-increase? Well, because if we add 0, that allows it to not increase. So it's either decreasing or stays constant. So with that said, this is not exactly an alternating series because we go from negative to 0 to negative to 0 to positive. Honestly, it's right here and therefore, or thereafter, we have alternation. So we can turn this into an alternating series, and that's actually what I have in my notes. This is just an opportunity to say, sometimes we have functions which are a little weird. Functions are weird. Can we change it into an equivalent series? So this is a skill that I hope to begin to build with you, but eventually you'll perfect in higher levels of mathematics. So I'm going to change this to an equivalent series, saying I really do not want any of my even terms. If I don't want any of my even terms, that's where I am going to replace the n with 2n minus 1, because then the first term still stays 1, the second term is 0, so it's not really included. The third term from up here is really going to be the second term, right? Or really, it's kind of built into the third term right here. So that way we can rewrite the series just to have an equivalent series, but we don't actually have to, or we could use then the alternating series test. So let's go ahead and go do that. Derivative of the numerator there is smaller than the derivative of the denominator. Hopefully you know that a linear function is smaller than has a smaller derivative than the quadratic function. So it's this is a decreasing function. We could say non-increasing. This is specifically a decreasing function. The limit as n approaches infinity of that part of the rule that a sub n is 0. Therefore, we have convergence. And why do we have convergence? By the alternating series test using that series. Am I going to make you rewrite a series like this one into this one? No, I'm never going to do that. This is really more of an exploratory problem. So then we say, okay, if we have an alternating series, we know that it has convergence, but what is the actual sum? Kind of going back to how I began, I said, okay, our goal is to be able to find the sum. So can we find the sum of the series? If it's geometric, we have a specific rule that allows us to find the sum. If it's not geometric, all we know is convergence or divergence, but we don't know what the actual sum is. However, we can approximate that sum in different ways. So if you remember, when we did the integral test, we said the remainder, and just as a quick reference, the remainder is if we take the difference between the sum and the partial sum. So that remainder has to be less than the integral from n to infinity. So that allows us to say that the integral, and then the integral is going to be bigger than the Riemann sum. So therefore, we're bounded by the integral from there on after. When it comes to the alternating series test, the alternating series test says the remainder is now bounded by the next term. So what I did on the notes here was I showed why the next term and does it actually work. So I found the first partial sum, second partial sum, third partial sum, etc. When it came to the first partial sum, I found my remainder. So 1/2. So if we look at 1/2, the next term, let me go ahead and write out the series because it's not exactly shown. So the first term is a positive 1/2. Second term is a negative 1/4. Third term is a positive 1/8. Fourth term is a negative 1/16. And I'm kind of running into the work that I did before. So that's my series written out, or at least the beginning of the series. And let me clean up that negative 1/16. So 1/16 plus 1 over 32, and so on. So the first partial sum, if I look at the difference between the actual sum, and I do know the actual sum because this is geometric, the actual sum is 1/3, so positive 1/2 over 1 minus negative 1/2 ends up giving us 1/3. So the difference between 1/2 and 1/3 is 1/6, which is less than the next term. Then if I add those two together, the second partial sum is 1/4. The difference between 1/4 and 1/3 is 1/12, which is less than the third term, which is 1/8. I could do it one more time, that if I go ahead and get my next partial sum, my third partial sum is 3/8. Difference between 3/8 and 1/3 is 1/24, which is less than the next term of 1/16. So you can see that this is working, but why does it always work? Because if we combine the next term with the term after that, we will get a number that is smaller than the 1/8 because they're alternating. So if we have a positive 1/8 and negative 1/16, this is why decreasing is kind of important, that they cancel each other, or we get a smaller number than what we had to begin with. And if you look further, this one's negative 1/16 and 1/32 is still going to be significantly smaller than the 1/8. So we're getting significantly smaller numbers. So we are bounded, or the remainder is bounded by the next term, and that's the absolute value of the next term. Keep in mind that. So for the problem I have here, let's approximate the sum by finding the first four terms. I am also like adding some directions here. Let's go ahead and bound the sum. So the fourth partial sum ends up being 5/8. You can see and do the math right there. But then I want to bound it. So to bound my sum, it's going to be the fourth partial sum plus the next term, or minus minus the next term, just kind of like as boundaries. So if I take 5/8 minus the 1/20th and 5/8 plus the 1/20th, I know my actual sum has to exist between those two numbers. So there is another error that we're going to be doing this chapter, that is Lagrange error, or Taylor's error. We'll get to that at some point, but all three errors are something that you have to be prepared for when it comes to taking the test. Which one is most often used? Excuse me. The alternating series is the one that I see the most. However, I do see the other errors occurring on the AP test. So then we say, okay, we have convergence or divergence. We use the alternating series test to determine what's happening. But with alternating series, there's something special that's going to come out of this, and we're kind of setting a stage for some skills that we'll be using when we get to what we call Taylor series. So that skill is going to be absolutely convergent or conditionally convergent. So let me take the math out of it to say we have absolutely convergent if our series is going to converge whether it alternates or not. So if it didn't alternate, if that series converges, that is absolute convergent. If the series diverges without the absolute values, so if the series diverged, then the alternating series converged because it alternates. So our conditional convergence is converging because it alternates, where absolute convergence is it converges regardless. So therefore, it doesn't really matter if we have the alternating or not. So I did skip around when I came to this problem. I actually want to talk about example number 8 first. So when I take a look at this series is going to be -1, and then plus 1 over the square root of 2, then minus 1 over the square root of 3, plus 1 over the square root of 4. Now we can see that this is going to, that our series, the next term is going to be less than or equal to the previous term. That's again without the alternating part. And then the second is the limit as n approaches infinity. The base of n is 0, so this is true. So by the alternating series test, this converges. So by alternating series test, this converges. Now, if I take out the alternating parts, I have the 1 over n to the 1/2. We know this diverges by p series. Since this diverges by the p series, but the alternating series says it converges, this, which by the way, I do have right here. I should have seen that. But anyway, this is a conditional convergence because the only reason why it converges is because of the alternating series. If I look at example number 9, this is one very similar to the previous problem. Hopefully we can see that this converges by the alternating series test because all I did was really make this n into 3 halves as opposed to n into 1 half. Since this converges by p-series and the other one converges by alternating series, then we can say that the sum that we care about actually absolutely converges. So let's go ahead and look at example number 7. As I said, I'm skipping around a little bit. What I want to do initially is, let's go ahead and write out the terms, -1 over the natural log of 2, 1 over the natural log of 3, -1 over the natural log of 4. I could see that the limit approaches 0. I could also see that this is going to be a non-increasing function because the numerator doesn't change and the denominator is getting bigger. Therefore, it has to be a decreasing function. Now, what happens to a sub n? And 1 over the natural log of n plus 1, I had some students who said, hey, I know that's going to diverge because of the integral test. My question is, how do you integrate that? Now, it's possible to integrate this, but this is not something that we've done in class. So please don't use the integral test on this because this is not a commonly integrated function. Now, you're welcome to use the integral test if you actually show the integral. Yeah, so be it. I'm totally okay with that. If you show the integral and show the integral diverges, life is good. What happens if it's not something that you could do very easily? Then, okay, let's try to find another test. So let's compare this to something simple, and I chose 1 over n. So 1 over n is smaller than 1 over the natural log of n plus 1 because this n is going to grow at a faster rate than the natural log. So since n grows at a faster rate than natural log does, then this becomes a smaller number, 1 over that number, the smaller. Once again, it's all about the number sense. So what I have in green, this series I have in green, should be smaller values than what I have in blue. 1 over n, we know diverges by the p-series. I didn't write down why, so this diverges. So 1 over n diverges by p-series. Therefore, the one that we're looking for, the 1 over the natural log of n plus 1, also diverges, and that diverges by the direct comparison test. I know I have that written up there. So by the direct comparison test, and once again, that the smaller diverged. So since the smaller diverged, the larger one has to diverge. But this one will converge by the alternating series test. We also said that. Therefore, we have conditional convergence. This is going to be a classic case of our goal is just to determine, does it converge conditionally or absolutely, or does it diverge? The answer is not so simple because we have to go through a series of logic to get there. Now, my hope so far is that you've been able to follow all the logic because I've been trying to set this up in a how should we approach this. If you have any questions, please reach out to me. Very happy to answer those questions. So, last but not least, I gave this problem. Now, when it comes to this problem, this is not a true alternating series. The reason why it's not a true alternating series is because it doesn't exactly alternate. We have a negative, then a negative, then a positive, then a positive, and that has to do with this n times n plus 1 over 2. We could go into detail about that, but not at the time or place part. So this isn't a true alternating series. What we could do is we could lump the first two terms together, the second two terms together, kind of like what we did when we had, it's escaping my mind right now, when we had telescoping series. So we can group those together, sort of like what we did with the telescoping series, to turn this into a new alternating series, like I did up here. So we can do that, but that's more work than what we really need to. So what we can do is we could say, okay, let's go ahead and take the absolute value of the function we're looking at, which if we take the absolute value, this is 1/3 to the n essentially, which converges by a geometric series. So if the absolute value of that converges, then we know that that series is going to be absolutely convergent as well. So while we could have done a lot more fun work, we don't have to. And so I know there's some people out there rejoicing. Mathematicians out there are all crying because, hey, we would love to see that too. All right, then we get to our last test, our last series of tests that we're going to be working with. And those last series of tests are going to be the ratio and root tests. So the ratio test. What we say with the ratio test is we will take the limit as n approaches infinity of the series with n plus 1 plugged in, so the next term over the previous term. And when I look at this next term over the previous term, I have to pause and say, where have we ever compared the next term over the previous term before? Oh yeah, geometric series. So what we are doing is by finding the next term over the previous term, we are modeling a geometric series. And in essence, we are doing a hidden limit comparison test to a geometric series. Now, is it really a geometric series? No, but it's going to be a limit comparison test to see what exactly is going on. So when we do this limit comparison, we're comparing it to a geometric series. And if you remember with the geometric series, I know I said it earlier, if the absolute value of the ratio is less than 1, then it converges. If the absolute value of the ratio is greater than 1, then it diverges. Well, by doing the limit comparison here, if the limit's less than 1, so if we get some limit L, if that limit's less than 1, then we have absolute convergence. If the limit is greater than 1, we have absolute divergence. So we're using the limit to compare it to a geometric series, even though this isn't really a geometric series. Hopefully that makes a little bit of logical sense to you. Now, by the way, if the limit equals 1, it's an inconclusive test. We have to do something else. So for our first problem, it's always good to have a general idea of what's going on. Which grows faster, exponentials or factorials? Great question. I'm not sure if we've addressed it in the videos. I know I've talked about it in different classes, but this ratio test allows us to formally prove what's happening. So if we take the limit as n approaches infinity of the next term, see I plugged in the n plus 1, divided by the previous term, which is just plugging in n. Anytime we do this, I strongly encourage you to multiply by the reciprocal because that's what we do with fractions. And then if you remember 5 to the n plus 1, we can write as 5 to the n times 5. Those are some exponent rules. N plus 1 factorial, we can write as n plus 1 times n factorial. Those are some factorial rules. Then what cancels gives us the limit as n approaches infinity of 5 over n plus 1, which is 0. So by the ratio test, this will converge. On our second problem, which grows faster, an exponential or a polynomial? Hopefully you know the exponential will grow faster. Therefore, we could say this should diverge. So it's always a good idea to get an idea of what's going to happen to the problem beforehand. Let's go ahead and use the ratio test to prove what's happening. I know we could probably use the nth term test on this one. There are lots of different tests we could do. I'm just trying to show you a situation where our limit is greater than 1. So that 3 is going to be greater than 1. So the ratio test, if we plug in n plus 1, now if you notice, I jumped immediately to multiplying by the reciprocal. Totally okay with that, everybody. If you want to do that too, more the power to you. I know this kind of cheats that we're really doing a limit comparison test to it. So it's cheating that mentality, but as long as you remember that's what's happening, okay. We do some simplification, and that's where we say the limit as n approaches infinity of 3 times n cubed over n plus 1 cubed. That limit does equal 3. So we have divergence by the ratio test. Problem number 3, we do know this converges by a p-series. So once again, why am I doing this? Because I'm trying to show a relationship that if we take the n plus 1th term and divide it by the nth term, which we multiply by the reciprocal, then this limit does equal 1, which is where we have an inconclusive test. So it's inconclusive because the limit equals 1. And I'm showing you it's inconclusive here. That we do know that the series we want converges, but if I take example 3b, if I take the series 1 over n, of course that diverges by p-series. But if we do our ratio test, that limit is also 1. Therefore, we have an inconclusive test as well. So just because the limit equals 1, that doesn't mean we know anything. It could be either convergence or divergence, as I showed here. On to the last problem, and this is going to be a little bit more typical problem for what you would use the ratio test for. So when it comes to the ratio test, my question is, what happens if I take something that's sort of geometric in nature and multiply it by a polynomial? Is that sufficient enough for us to have convergence over divergence, or really divergence over convergence? So let's find out. Plug in n plus 1, and then divide by plugging in n, which means multiplying by the reciprocal. And just like before, we should have some cancellation. So this is 3 to the n times 3, so the 3 to the n's cancel. The n 2 to the n plus 2 over 2 to the n plus 1 gives us 2. So the limit as n approaches infinity ends up being 2/3. So that 2 verges means we have convergence by the ratio test. So that question that I asked from the beginning is if multiplying by polynomial is going to be sufficient enough to make it diverge, and the answer is no. It's still going to converge. Last but not least, we have our root test. Now, when it comes to our root test, if we have two functions that are taken to the same power, in this case we see that both of these are taken to the nth power, then what we're going to do is we are going to eliminate that common power and figure out what happens with the rest of the problem. So if the limit, in this case, ends up being 0, we're going to have absolute convergence. Now, we can see that by the rules we have listed, but the question really becomes why. So the idea behind this is we are going to say, what is the limit as n approaches infinity of e cubed over n, but that whole limit's being taken to the nth power. So this allows us to say, in essence, we have 0 to the nth power. And since that ratio, it's not really 0, but it's something very close to 0. Since that ratio is less than 1, which we see right here, if that ratio ends up being less than 1, so the ratio is less than 1, and that ratio being the overall limit, then we have convergence. As I look at this problem right here, I'm applying the root test. So once again, if I decide to take this nth root, and let's take that nth root and bring it out in front of the limit, then we're really saying this limit to the nth power. And so once again, we're sort of modeling a geometric series by saying, let's take the power out of it, see what happens on the inside. And with that happening on the inside, if that limit, aka ratio, is less than 1, it converges. If it's greater than 1, then we have the divergence. So since this limit ends up being 1/2, then we have absolute convergence. And now let's pull it all together. So what I did was I listed at the top, nth term test, geometric series, integral test, p-series test, direct comparison, limit comparison, alternating series, ratio, and root test. Those are all the different tests that we get to choose from as we approach the problem. So when I look at example number 7, so on example number 7, my first thought should be, well, do I think this is going to converge or diverge? Well, because the powers are the same, so these are the same powers, then what am I expecting? I'm expecting divergence. Now, if you don't know that, that's okay, but I'm just trying to talk through my thought process on here. So since I'm expecting divergence, well, the nth term test allows us to test for divergence right away. Now, on the next one, this looks like a geometric series. So it's a geometric series. Therefore, let's take a look at the ratio. Pi over 6 is less than 1. Since pi over 6 is less than 1, we do converge by the geometric series. What's our next problem? I'm trying to hide it from you. So our next problem is, what happens if I have this series? Well, if I have this series, my initial thought is, okay, I can't really do an nth term test on this one. I do have n over e to the negative n squared, but that if I take that limit and use L'Hopital's rule, that's going to be 0. So, and then my initial thought is, this looks very integrable. And since it's very integrable, that's set up beautifully for us to do the integral test. So that's what I did. I included my scalar on that. So integrated through u substitution and then take the limit as b approaches infinity from 1 to b. And since that ends up being something that it has an actual limit, since this has a value, then we know that we have convergence by the integral test. Let's try not to spoil the surprise on the next one. So on the next one, we have 1 over 3n plus 1. And my thought is 1 over n diverges. So this is probably going to diverge as well. Since 1 over n, and the reason why I said that is because we have the degree is 1 degree less than the denominator. So this is where we're going to use our limit comparison test. We're going to compare to 1 over n. And since our limit does equal 1/3, we have divergence. And since 1 over n diverges by p series, then the series that we're looking for also diverges by the limit comparison test. Onward and upward, guys. Example number 11. I see this one, and my initial thought is, what approach should I take? And this goes back to, I'm comparing factorials to an exponential. So in that comparison of factorials to exponential, I know that the most efficient way to show this test is going to be through the ratio test. Now, kind of like getting a sense for what's going on, which one grows faster, a factorial or an exponential? The answer is factorial. So my numerator should be growing faster, so I'm expecting divergence. How do I prove that efficiently? Well, because everybody, what's the derivative of a factorial? Yeah, we don't know that yet. So this is where I'm going to use the ratio test. And you can see the work that I did on the ratio test here. And since that limit's infinity, we do have the divergence that I mentioned. And finally, example number 12. -1 to the n times 3 over 4n plus 1. This one just screams alternating series test, so that's what I'm going to do. So once again, I showed the limit n approaches infinity is 0. This is not increasing. I showed that through the L'Hopital mentality. So by alternating series, this does converge. Now, does this converge absolutely, or does it converge conditionally? So if we take a look at the 3 over 4n plus 1, we can then use the limit comparison test to compare that to 1 over n. Which, since 1 over n diverges, this one will also diverge. Therefore, we have conditional convergence. All right, everybody, I had a lot of fun with this. I hope you did too. And I'm looking forward to introducing Taylor series to you. And yay. All right, bye.